Hello and welcome. In the previous lecture, we talked about how we can draw a line of best fit through a collection of data points using the method of least squares to draw a linear regression line. In this video, we're going to talk about how we can take information from a sample and the output from performing a linear regression to make inferences from our sample to a broader population. So this is the same thing that we've been talking about throughout this class. We want to know how we can take what we know from our sample and generalize to a broader population that we're interested in, because most likely we don't have data from the entire population, and so we want to be able to talk about relationships between variables based on the information that we have in our sample to say something about broader research questions that we have. So in this lecture, we're going to talk about the methods that we have for doing that with linear regression. The example that we're going to be talking about throughout this video comes from this 1966 paper called The Genetic Determination of Differences in Intelligence, a study of monozygotic twins reared apart. So the data that we have from this paper is data on IQ scores for these 27 pairs of identical twins. So for each of those pairs, and each observation in this study is a pair of twins. So for each of those observations, we have an IQ score for the twin who was raised by biological parents and the twin who was raised by foster parents. And the question that this paper is trying to get at is whether people's intelligence is determined more by nature, by sort of innate biology, or by nurture, by how the child is raised in the particular environment in which they're raised. And so one interesting way to try to get at this question is to compare pairs of identical twins who, because they are identical twins, because they share all of these genetic similarities, the nature component of this nature or nurture question is pretty much the same. And what is different among those twins is the situation in which they were raised. So if the IQ scores of the twin raised by a foster family and the twin raised by biological parents, if those IQ scores are really closely related to one another, that might be evidence that there is a strong natural biological component to intelligence. So that's what this study was trying to get at. And in this data, there is a correlation between foster IQ and biological IQ, so the IQ of the twin raised by foster parents and the IQ of the twin raised by biological parents. The correlation between those variables is 0.88, so that is a pretty strong correlation. So you can see in this graph here, we've drawn the line of best fit through these data points. We have the IQ of the twin raised by foster parents on the y-axis, making that our dependent variable, and we have the IQ of the twin raised by biological parents on the x-axis, making that the independent variable. So moving on to looking at what R returns to us when we estimate a linear regression in R, we're going to take a look at this output. So we set up this regression in R so that the dependent variable is the IQ of the twin raised by foster parents, and the independent variable is the IQ of the twin raised by biological parents. And we want to know if the IQ of the twin raised by biological parents can predict the IQ of the other twin. So we talked in the previous video about how we would calculate the intercept and the slope of the line, things like that. When we estimate this regression in R, we're going to just go ahead and get those parameters given back to us. So based on this sample of 27 pairs of identical twins, we have an intercept of 9.208 or so, and a slope of 0.901 for this independent variable that we're looking at. R is also going to give us standard errors around the intercept and the slope coefficient. It's going to give us t-statistics and p-values for those t-statistics. And then in the output below, we also have the R squared value. This is multiple R squared, so 0.7779 in this case. So let's talk a little bit about how we would use this output to understand whether there is a statistically significant relationship between our independent variable and our dependent variable. But before we do that, we need to make sure that we understand what we're asking. And the best way to do that is to think about what our hypotheses would be when we do a hypothesis test. So, assuming that all of these 27 pairs of twins are a representative sample of all twins separated at birth, we would like to test if the data provide convincing evidence that the IQ of the biological twin, that is the twin raised by biological parents, is a significant predictor of the IQ of the twin raised by foster parents. So take a look at these sets of hypotheses and see which one you think is appropriate. So to know about the relationship between these variables, we want to be looking at the slope, so that's beta 1, and also our hypotheses are going to be about the population that we're interested in, not our sample. So when we're dealing with our sample, the B0 and B1 statistics from the sample refer specifically to the data that we collected in just the sample. Beta 1 and beta 0 are population parameters. So this last set of hypotheses, the null hypothesis being that beta 1 is equal to 0 and the alternative hypothesis being that beta 1 is not equal to 0, is the appropriate set because it is dealing with the population parameter for the slope of the relationship between these two variables. So here again is this information that we got when we estimated the regression in R about our estimates for each of those parameters, our standard errors, our t-statistics, and our p-values. So when we're doing a linear regression like this, we're going to use a t-test to do our hypothesis test. So we're going to be referring to the t-distribution. So the test statistic for a t-test is our point estimate minus our null value divided by the standard error. The point estimate that we're interested in is this B1 value that we calculate, so the observed slope of the relationship between these variables in our sample. That's going to be our point estimate for the population parameter that we're interested in. Then the standard error associated with that, so that's 0.0963 from this output. That's the standard error for this bio-IQ variable. That's the standard error around this estimate of the slope. And then the degrees of freedom that we need for our t-test is equal to our sample size minus 2. So we have 27 pairs of twins, so n is equal to 27, and our degrees of freedom are going to be n minus 2, so 25 degrees of freedom. So keep in mind, we lose a degree of freedom for every parameter that we estimate. So in this simple bivariate linear regression, we're estimating the intercept, which is one parameter, and the slope coefficient for bio-IQ, which is a second parameter. If we put another independent variable in the model, we would lose another degree of freedom. If we put another independent variable in the model, we'd lose another degree of freedom. So every parameter that we estimate, we're going to lose a degree of freedom for. So again, in this case, we're estimating the intercept parameter and the slope parameter, so we have degrees of freedom equal to n minus 2. So let's go over how we would look at this regression output to do our hypothesis test. So we're going to calculate our t-statistic first. So t is equal to our point estimate minus our null value divided by our standard error. So our point estimate comes directly from this regression output. It's equal to 0.9014. So that's our point estimate from the sample for the slope parameter for bio-IQ, minus the null value. Remember, our null hypothesis is that there's no relationship between these variables. When there's no relationship, the slope is equal to 0. So we're going to say minus 0 in the numerator of this t-statistic formula. And then we're going to divide by the standard error, also from the regression output. So divide by 0.0963. And that's going to give us a t-statistic of 9.36. So we've gone ahead and solved out that t-statistic, but you can actually see that in the regression output. It's also coded, color-coded orange. So under t-value for bio-IQ, there is that t-statistic of 9.36. So we know that we have 25 degrees of freedom. So if we go ahead and go to a t-table, or if we solve for the p-value using R, we're going to find a p-value of less than 0.01. And in fact, you can see that p-value also in this regression output. So under probability of a value greater than t, that final column in the regression output there, the associated p-value is 0.0000. So a really small p-value, which means a really significant result. So we don't have to go through this process of solving for the t-statistic and solving for the p-value because all of that information is given to us in this regression output. But I want to make sure you understand where those numbers are coming from when R returns that output to you. And again, in the lab for this week, we're going to go over how you actually input a linear regression formula into R and get this output. So this is what R would give back to you if you estimated this particular regression, and here's how you would use it and interpret it. So in addition to doing a hypothesis test, we might also want to estimate a confidence interval around our point estimate of this slope parameter. So a confidence interval is a point estimate plus or minus a margin of error. Now remember, when we're doing a linear regression, we're going to be using the t-distribution. We have 25 degrees of freedom and minus 2 degrees of freedom. So take a look at some of these options below and see if you can figure out which one is the correct formula for finding the 95% confidence interval for the slope parameter that we've been working with. Okay, so we have this formula of a confidence interval plus or minus a margin of error, and our margin of error is going to be a critical value times a standard error. So first of all, we want to make sure that we're looking at the right point estimate. So this is the slope parameter point estimate for bio-IQ, so 0.9014. Plus or minus a critical value. Now remember, we're working with the t-distribution, so the critical value for a t-distribution with 25 degrees of freedom for a 95% confidence interval is 2.06. So we have our point estimate plus or minus 2.06 times our standard error. And that standard error, again, is going to come directly from this regression output. It is 0.0963. So the correct way to find this confidence interval is to take 0.9014 plus or minus 2.06 times 0.0963. So that's a confidence interval from 0.7 to 1.1. So with 95% confidence, we can say that the population parameter for the slope of the linear relationship between these two variables is between 0.7 and 1.1. So this slide is just a quick recap of how we use our output from a linear regression to do inference, to do a hypothesis test, or to construct a confidence interval around a point estimate that we find. So this is just review. We just talked about all of these things. Usually when we are doing a hypothesis test, our null value is 0. So when we have a hypothesis about the slope, our null value is that the slope is 0, that there's no relationship between our independent variable and our dependent variable, and usually our alternative hypothesis is a two-tailed hypothesis that says that the slope is not equal to 0. And the regression output is going to reflect this. The regression output is going to return a two-tailed p-value for the t-test that we did for the slope parameter. So if you want to do a one-tailed test, you're going to have to convert that p-value that R gives you. Or there are options when you actually estimate the regression. You can have R return a one-tailed p-value if you want. But that's just something to be aware of. If you have a hypothesis test that is directional, if your alternative hypothesis is that the slope is positive or that the slope is negative, then you have to make sure that you're doing the correct test and finding the correct p-value. And we're usually not going to be doing inference based on our intercept, so that's why the focus of this lecture video was on the slope. If you do want to do inference based on the intercept for some reason, you also have the point estimate for the intercept and the standard error for the intercept, so you should be able to follow the same procedure. But usually what we're interested in is the slope of the relationship between a dependent variable and an independent variable. And I want to end this lecture on just one final note. You should always make sure that you understand what the type of data you're working with is. Whether you have a random sample or a non-random sample matters a lot for whether you can make inferences from your sample to the general population. And if you happen to have data on your entire population of interest, then you don't go through this procedure of finding confidence intervals and things like that, because you're not making inferences from a sample to a population if you already have population data. So it's important for you to know what kind of data you're working with. And then if you have a sample that it is not random, then you can't make inferences that are reliable from the sample to the whole population. So we've talked about this in quite a bit of detail in earlier videos, but I just want to remind you, none of these underlying principles change when we're dealing with this linear regression framework. Our ultimate goal in statistical inference in general is to have independent observations, and the best way that we can make sure that we have that is to take random observations of a sufficiently large sample size. So those are the best ways to make sure that our observations are independent of one another so that we don't end up with biased results. And that brings us to the end of this lecture on inference based on linear regression. Thank you for listening, and I will see you next time.